Okay, on the 6.1 quick check, we're talking about exothermic and endothermic. So we need to look at different situations and be able to classify them as exothermic or endothermic. Okay, when it says Q is greater than 0, that means Q is positive. Okay, I always think back to, uphill and downhill graphs. And the idea is that is always the final heat minus the initial heat. So if I have a big number minus a small number, that's going to be positive. So that's endothermic. So uphill gives me an endothermic positive Q. Heat is released. Heat is released, that's just a definition of exothermic. Molecular attractions are strengthened. Okay, attractions are strengthened. This is one that I personally have a little trouble with. So I'm thinking about this. If I want to strengthen attractions, where does energy go? I can think of it easier the other way. If I wanted to break some attractions, I want to weaken some attractions, that's going to require energy. That would be endothermic. So if they are strengthened, then I'm going to say that that is exothermic. Okay, so if I think of it backwards and I say, okay, I want to weaken some attractions, I want to tear things apart, that requires energy. So when they go back together and become stronger, that gives off energy, exo. Okay, heat on the right side, that's heat given off, that's exo. Okay, Q is less than 0. That means Q is negative. If Q is negative, again, I think of this, what's going on? Okay, I've got a small number minus a larger number. Okay, so that is exothermic. Okay, Q is negative, that's exothermic. Bonds are formed. Okay, again, bonds are formed, that's a toughie. If I wanted to break bonds, that would require energy, that would be endo. So bonds formed, that's exo. Okay, bonds forming is going to be exo. Heat's on the left side, that means I got to put heat in. Heat is going in, so that's endo. And heat is absorbed, same thing, endo. Okay, and that's the first little part. Now, what about these pictures? Okay, heat's on the left. I'm putting heat in, energy into A to get to B. So I'm starting low, I'm putting energy in, and I'm getting to B. So this is A and this is B. This is uphill. Heat on the left, uphill, endothermic. Okay, heat on the right means I'm starting at A, okay, and I end up low at B, and the heat must have been given off for this reaction, so I'm dropping down, so A going down to B. Okay, if heat's on the right, then I must be going downhill. So heat going in, uphill, heat given off, downhill. Specific heat. Now, the really helpful thing for this is think about specific heat as how much a substance resists change in temperature. Resists change in temperature. So if each of these little stories, you got to decide, is block A or block B resisting change in temperature more? Blocks A and B are made of two different metals but have the same mass. When 600 joules of heat is added, block A increases by 80 degrees while block B increases 30 degrees. Who is resisting change more? And it's B. Okay, because it only goes up. You put the heat in, it only goes up 30 degrees. So B is the one that has the greater specific heat. Blocks X and Y are made of two different materials but have the same mass. In order to heat the blocks from 20 to 50, block X requires 100 calories, while block Y requires 400 calories. Okay, who is resisting change more? And it's block Y. It takes 400 calories to get it to raise the same temperature, so Y is resisting change more. So Y has a larger specific heat, CP, than X does, and B had a larger CP than A does. So resists change in temperature. Think of that, and you can solve these kind of problems. Okay, calorimetry, a little calculation. So for each problem, list the variables. Okay, so when we see that there is some substance cooling down or warming up, then we know the equation is Q equals M delta T Cp. Okay, the mass times the change in temperature times the specific heat. So to solve these, we got to look for our variables. And we look at our problems here. So calculate the value of Q. Okay, we're looking for Q, so we know that's X. That's good. Okay, 35-gram piece of glass. So whatever, 35 grams is whatever we're warming up or cooling down. That's glass. Cooled from 128 to 85. Okay, so this is a little bit tricky, and the idea is it's always final minus initial. So it's 85 minus 128, which is negative 43 degrees Celsius. Okay, so that means when I'm done, I'm going to end up with a negative Q. So the signs on delta T and Q come out the same. And it makes sense that if Q is negative, we were talking about before, that means it's exothermic. And if the glass is cooling off, then it must be releasing energy in order for it to cool down. And the CP that's given to us is 0.84 joules per gram degree Celsius. And we can see, okay, things are good. Degrees and degrees. We've got grams and grams. Our answer is going to be in joules when we're done. So now it's just a matter of substituting and evaluating the expression. So Q equals M delta T C sub P. Okay, that's an equal sign. And mass is 35 grams times the change in temperature, negative 43 degrees Celsius, times 0.84 joules per gram degree Celsius. So grams drop out, degrees drop out. So 35 times negative 43 times 0.84 equals negative 1264.2 joules. So negative 1,264.2 joules of energy is given off, released by this glass as it cools down. Now another problem, what is the mass of a block of lead if 500 joules of energy is required to increase its temperature from 50 to 110? Okay, so again, we're warming something up, so the equation is going to be Q equals M delta T C sub P, and we got to find our variables. Okay, so what is the mass of a block? Okay, so we're looking for the mass. If 500 joules, so here we have 500 joules of energy, is required to increase its temperature from 50 to 110. So a final minus initial, that's going to be a positive 60 degrees. And that makes sense because a positive energy is needed to warm something up. And the C sub P is given, okay, 0.129 joules per gram degree. Okay, and we see that's a pretty small number. That's easy to warm up and cool down some lead. Okay, so we're going to substitute in. So 500 joules equals X times change in temperature 60 degrees times 0.129 joules per gram degree. So degrees drops out, joules are going to drop out. So this answer is going to end up being in grams, which makes sense. Okay, now we get to do a little math. And we just say, okay, I want to get X by itself, so I'm going to divide both sides by 60 and 0.129. So I'm going to just skip here and say 500 divided by 60 and divided by 0.129. And then we know that's going to be in grams. And that comes out to 64.599 grams of lead. Okay, I would probably round that off to 64.6 grams, just because it's a little easier to look at. Okay, so again, it's just Q equals MC delta T, M delta T C sub P, and we just find our variables and substitute in and get our expression, get our answer. And that is the quick check.